Now we talk of admissibility of A star. The A star algorithm, depending on the heuristic function, finds or not an optimal solution. If the heuristic function is admissible, optimization is guaranteed. A heuristic function is admissible if it satisfies the following property. For every n, the Hn is bounded by 0 and H star n. That means Hn has to be an optimistic estimator. On the other hand, it never has to overestimate H star n. Using an admissible heuristic function guarantees that a node on the optimal path never seems too bad and that it is considered at some point in time. A star guarantees an optimal solution if Hn is an admissible heuristic and the search space is a tree. Now Hn is admissible, as I told you in the previous slide, if it never overestimates the cost to reach the destination node. A star generates an optimal solution if Hn is a consistent heuristic and the search space is a graph. Now Hn is a consistent heuristic if for every node n sub I and for every successor node n sub j of n sub I, we have Hn less than equal to C of ni nj plus h of nj. This is what I mean, that the estimate that I make of reaching nj, the estimate about nj to the goal and about ni to the goal should take into account the cost of coming from ni to nj. If that happens, then we have a consistent heuristic. A star expands nodes in order of increasing f value. And what really happens is that it gradually adds the f contours one after another into its search space. And as it encounters gradually f contours of nodes, it goes towards more promising nodes. We would now look at the optimality of A star and prove it by an intuitive method. Let us say we have a suboptimal goal G2 in the fringe and we have a node n which is not yet expanded. Let n be in the fringe as well and let it be on a shortest path to the optimal goal G. Now A star is optimal if the heuristic value at n is less than the heuristic value at G f, the heuristic value at G2. Now we know that the f of G2 is equal to G of G2 because G2 is a goal and h of G2 is 0. Further, G also being a goal, f of G is equal to G of G since h of G is 0. Now we have been told that G2 is suboptimal. That would mean that the cost of coming to G2, which is G of G2, is greater than the cost of coming to G. Now we know that G of G2 is f of G2. Therefore, f of G2 is greater than f of G. Now since we are talking of an admissible heuristic, we know that h of n is less than equal to h star n, and therefore from this we could write that g of n plus h of n would be less than equal to g of n plus h star n. Now just to recall that g of n plus h of n is nothing but the heuristic function and value of the evaluation function f of n, and g of n plus h star n is f of g. So we could write here that f of n is less than equal to f of g, and given that f of g2 is greater than f of g, we can conclude that f of n is less than f of g2. So that is how we could say that A star is optimal, because any node that it picks up for expansion, the evaluation function at that node is going to be less than a suboptimal goal. Now we will focus on other interesting portion of today's lecture, which is about local search. So what are local search algorithms? In many optimization problems, the state space is the space of all possible complete solutions. Objective functions tells us how good a given state is. Find a solution by minimizing or maximizing the value of this function. These algorithms do not systematically explore all the state space. Heuristic or evaluation function reduce the search space, which are not worth being explored. Algorithms do not usually keep track of the path. The memory cost is minimal therefore. But one thing to be noted here is that the total lack of memory at times can be a problem because we may end up having cycles. Nevertheless, these are popular search algorithms. The local search uses single current state and move to neighboring states. The idea is to start with an initial guess at a solution and incrementally improve it until it is one. The advantages of local search is, as I told you, uses very little memory, find often reasonable solutions in large or infinite state spaces. It is useful for pure optimization problems, find or approximate best state according to some objective function. We will look at one such local search algorithm called the hill climbing search. The idea is similar to climbing a hill. So the surface looks like something of a hill with lot of ups and downs. And let us say we are here in our search. We can be using two different types of heuristic functions. We may estimate the distance from a peak to arrive at the peak. For such a heuristic estimate, the smaller is the better, or we may be using the height defined by the evaluation function. And as you can guess, in a hill climbing search, if I am talking of height, greater is better. So the hill climbing procedure, if you allow me to put, is very simple. You just initialize a state called current to the starting state, and then you initialize a state called next, which takes the highest valued successor of current. If the value of next is less than the value of current, we will return current, else we will let current equal to next, and this continues. So basically, if I am looking for reaching this point from here, I will look at my neighborhood and move to this point, which is possibly the best, and then make this my next point and increase my search space. So pick up this, move here, make my search space here, and I will slowly but surely reaching the height. But is it that simple? We will look at it in a minute. There are variants to the hill climbing algorithm. The simple hill climbing is a basic method in which the first state that is better than the current state is selected, as I was trying to explain this. There is other called the steepest ascent hill climbing, where we consider all moves from the current state and select the best one as the next state. So let us take our 8 puzzle game once more and see and understand hill climbing. Let us take this to be our start state, and here is our goal state. We will use again our heuristic function of the number of misplaced tiles. So we will try to expand these nodes and get the newer nodes, but then compute the number of misplaced tiles for each one of these nodes. So this has 5 misplaced tiles, this has 6, this has 4, and this has 5. So I would love to expand the one with the lowest number of misplaced tiles. I expand that node and end up having 2 more nodes here, and then we compute the heuristic values 5 and 3. Therefore, we opt to expand this node. This node is expanded and ends up in 3 more nodes. We compute the heuristic values. This node with the lowest heuristic value is expanded next. We end up having this node, and then that's expanded to reach to the goal. So if you give some thought to the whole process, this search that I was trying to do was about moving in a way in which the distance to the goal node was decreasing, and I did not take any other path. So that's the hill climbing search. The properties of the hill climbing search is that it terminates when a peak is reached, does not look ahead of the immediate neighbors of the current state, and this is what is important. Every time I was expanding the next level, I was only concerned at what are its successors and did not use any estimate of some measure of how far I am from the goal. It chooses randomly among the set of best successors if there is more than one, and does not backtrack, since if you remember, it does not remember where it's been. It does not keep a track of which state it came from. So this is good if your search space is really looking like a hill, but then it's not that. Search space features could be very complex, as shown in this figure. I have an objective function and the state space, and the state space versus the objective function curve is with many interesting properties. Here is the global maxima. Apart from the global maxima, we have local maximas, and then more interestingly, we have flat local maximas as well. Under such a state, if you are searching for just moving towards maximizing your return on the claim, and you are somewhere here in the current state, and your movement is towards this side rather than this, one would end up having this as the maximum, and we will miss the global maxima. This is a very, very serious problem with hill climbing. So drawbacks of hill climbing is that peaks that are in the highest point in the local space, the local maxima, we tend to get stuck there. State that is better than all its neighbors but is not better than some of the other states farther away would be what we would be stuck in. Plateaus, the spaces that has a broad flat region that gives the search algorithm no direction. The whole set of neighboring states that have the same value, not possible to determine the best direction. Like if you go back and look at that slide, here was a flat region completely, and here was another flat region. Now if I am somewhere here, or I do not know which state side to go to when I am on a flat region like this. So this is another drawback. And then there are drops off to the sides. Steps to the north, east, south and west may go down, but a step to one of the combinations may go up. So orientation of the high region compared to set of available moves and direction in which they move make it impossible to traverse reaches. So with these drawbacks, it is better that we now focus on one of the methods to overcome these, and that method is simulated annealing. Simulated annealing, the premise of it, the motivation of having it is because hill climbing algorithm that never makes it downhill is guaranteed to be incomplete. What it means is, if I keep on thinking of only climbing up and never think of climbing down again, then I will miss this global maxima. So what can be done is that we can think of random walks, but then purely random walk, that is moving to a successor chosen uniformly at random from the set of successors, may guarantee completeness, but is extremely inefficient. So we want to do better than this, neither remain incomplete nor want to have extreme inefficiency. So we combine hill climbing with a random walk in some way to get both efficiency and completeness. Simulated annealing is one such algorithm. Intuitively, what happens in simulated annealing, let me try to explain to you with this curve. So here is the state space and the evaluation function. Now, if you see, if my starting point is here and I was coming down this path, and if only I was looking at the evaluation function, then after this point I will have no more motion taking me out of this, and I will miss this global minima. So what can be done at this point of time is that I will occasionally take steps in different direction, from which the increase or the decrease, as the case may be, is maxima. So if I am here, with some probability I may be allowed to come up, and then there is a chance that I may end up going down this path and arriving at the global minima. So this is what is done in simulated annealing. It is a stochastic hill climbing algorithm. So a successor is selected among all possible successors according to some probability distribution. Now, the successor can be worse than the current one, but that is what I want. I do not want to monotonically only go towards one path and get stuck in a local maxima or local minima. Random steps are taken in the state space, and it is interesting to note at this point that this is inspired by the physical process of controlled cooling, crystallization or metal annealing, and that is why it is called simulated annealing. Metal annealing or crystallization, a metal is heated up to a high temperature and then is progressively cooled in a controlled way. If the cooling is adequate, the minimum energy structure, a global minimum, is obtained. This is what we want to achieve in simulated annealing. The goal of annealing, therefore, is to produce a minimum energy final state. But there is some probability that a transition to higher energy state will occur. This probability is given by this function here. Now, properties of physical annealing is used to define an analogous process of simulated annealing. Delta E here, the energy function, is generalized to reflect change in the value of the objective function. Analogy for kT is slightly different than the physical one. In the physical sense, K describes correspondence between the units of temperature and the units of energy. Here these units are artificial, and therefore the K is factored into T, and we use a more simplified equation like this. The best way to select an annealing schedule or change in temperature, as we want to do this, is to try several schedules and observing the effect on both the quality of the solution that is found and the rate at which the process converges. It is important to realize two things. As T approaches 0, the probability of accepting a move towards goes to 0, and simulated annealing becomes identical to simple hill climbing. What matters in computing the probability of accepting a move is the ratio of the energy to the temperature. Thus, it is important that the value of the temperature is scaled so that this ratio is meaningful, and this is something that one needs to really work on. Terminology from the physical problem is used here, as you have noticed. The temperature T is the control parameter. The energy E, or often written also as F, is the heuristic function about the quality of a state. The function F decides about the selection of the successor state and depends on the temperature and the difference between the quality of the nodes. That is, something that I select at one temperature, what is the evaluation function, minus what is the value of the evaluation function at a new temperature. The lower the probability of selecting, worst successes. The cooling strategy determines the maximum number of iterations in the search process, the temperature decrease steps, and the number of iterations for each step. So, here is the simulated annealing procedure. While the temperature is not 0, I would love to do a predefined number of iterations. Okay? I generate the successor of the current successor and look at their f values. Okay? Find that it is still greater than 0, then I take the actual to be the new one, and the temperature is decreased and this process is continued further. So, the main idea is that I take steps in random direction, but step taken in random direction do not decrease the ability of finding a global optima. The disadvantage is the very structure of the algorithm increases the execution time. However, the random steps possibly allow to avoid small hills, and that is a great advantage. The temperature, it determines through a probability function the amplitude of the steps, long at the beginning and then shorter and shorter. And annealing here is when the amplitude of the random step is sufficiently small not to allow to descend the hill, the result of the algorithm is said to be annealed. So, it is suitable for problems in which the global optima is surrounded by many local optima. It is useful for problems in which it is difficult to find a good heuristic function. Determining the values of the parameters can be quite difficult and often require experimentation. We have now covered the examples that we wanted to talk of in informed search. In our next lecture, we would be covering constraint satisfaction problems. Thank you very much.